here we focus on some resource objects, and we consider transformations of the resource object. And a resource theory generally defined by the set of free resources and the set of free transformations. While the definition depends on different resources, and especially the definition for the set of free transformations, there are many different choices. But for a general resource theory, given the free resource objects, there is a kind of a unique definition, which is called the resource non-generating transformations. So this is actually the largest set of free resource, because here a resource-free generation transforms a free resource to a free resource. So why we consider resource non-generating transformation? Because it is the largest one. So any free transformation, set of free transformations should be a subset. And generally, it gives like a very good analytical bounds. So let's first also review the definition of a resource distillation. Here we have some target state called rho, and so we have some quantum state called rho, and we have some target resource state called psi. And a single-shot resource distillation is defined by applying some free operation to rho, and we want it to be as close to the maximum resource as possible. And the single-shot distillation rate is defined by the maximum number of target resource we could obtain. So graphically, we can just see here that we apply free operation to rho, so that the output state is very close. It's an approximation of m copies of the target state. While there are actually many works studying resource distillation. And recently, especially in the past maybe five years, there are many works show that conventional resource distillation, they have quite significant limits. So for example, especially in the single shot region, there are many no-goes. So for example, we could not distill any pure state from states which are highly mixed, or not even when we have many copies of them, or not even we do it in a probabilistic manner. So this makes resource distillation practically challenging, right? So actually, if we just search for the experimental papers, we barely find experiments they really do entanglement distillation or like other resource distillations, right? So this challenge makes practical implementation of resource distillation kind of hard for the current technology. So a natural question is, can we kind of overcome these limitations by somehow bending the rules? And this is what we want to answer in this talk. So let's first kind of redefine resource distillation. So first, we need to observe that in many tasks, what we really want is not the quantum state, right? Generally, we measure the quantum state. So what we really need for many tasks is to have the measurement outcome of the target quantum state. In this case, if we kind of consider a less restricted requirement of obtaining quantum state to obtain measurement statistics, right? So here we consider that we only, so for example, here we consider that for observable M, instead of have a kind of approximation of the target pure state, we only want to approximate the measurement statistics. So graphically, this is equivalent to that we have the quantum state rho prime. So in the original definition, we want rho prime to be close to psi m. But here we assume that we also perform measurement of the state. So we require that the measurement statistics, they are close to each other. Well, if we require that this definition holds for arbitrary measurements, then you can easily prove that this requirement is essentially equivalent to the previous one, right? Because because if the two states if they are far away, then you could find some like measurements so that their measurement outcomes they are also very different. So here actually we have not extended the resource distillation framework. So this one is actually equivalent to the conventional definition. But we can do some further step. So notice that the measurement outcome, it is a classical result, right? It's not a quantum state anymore. So we can further apply classical post-processing on the classical outcome. A very natural classical post-processing is a linear combination of the classical results. So imagine we have like many different choices of free operation, and we linearly combine the classical outcomes with coefficients on the J. Right, so this is definitely doable because we can just combine the classical results. And then we can rewrite this equation into this one. So it looks like that we could apply some like a linear combination of free operations to the quantum state rho. So for simplicity here, we also group the operations with positive or negative results as two different groups. So here we denote the lambda plus minus to be the ones with corresponding positive or negative coefficients. And then the requirement that the two measurement outcomes they are close becomes to this one. Right? So here basically we put this linear combination of results into this one, and we group the positive and negative part. And the previous requirement becomes this one. And again, suppose that we require this condition holds for arbitrary measurement outcome. Then it is equivalent to our virtual distillation condition. So here the virtual distillation condition is that we can apply some kind of a virtual operation, which is not like CPTP map anymore. It could be a linear combination of free CPTP maps. And then we require that the virtually kind of manipulated state is close to the target state. Right, so if we just focus on the quantum state, not the measurement statistics, this is not possible. But if we focus on the measurement statistics, this becomes possible. So here, graphically, it's equivalent to this one. So we have an initial state, then we apply different free operations, and then we measure these two output states, and then we can linearly combine them. And we can prove that, so here, this condition is equivalent to the measurement statistics. They are always close to the measurement statistics of the target state. And yeah, so actually, based on the definition of the virtual operation, actually, we can easily, kind of quite straightforwardly, find that we can implement them in a probabilistic way. Right, so here, we define the P plus minus to be the normalized lambda. So here the lambda, gamma is the sum of the positive and the negative coefficients. And then this linear combination of measurement outcome comes this one. So here, since P plus and P minus, they are normalized, so we can make use of a Monte Carlo approach to implement this plot. So basically, in experiments, what we can do, we can first flip a bias cone with probability p plus. We have we do this part, and with probability p minus, we do this part. And when we get measurement outcomes, we just multiply this gamma, and also if for this part the sign is positive, for this part its sign is negative, and then we just average them. So in this way, we could effectively experiment to obtain the linear combination of operations. But we could easily find that this is not for free, right? Because here we multiply the gamma or minus gamma to the measurement outcome. So the measurement result, the range of the measurement result is kind of larger than the original one. So for example, assume the original measurement is a bounding operator like this. Since we multiply gamma or minus gamma to the outcome, so the range of the random measurement will be larger. So suppose gamma is at 1000, then it's a much larger range, which means that we need to make more measurements, right? So here the random variables, they are bounded in between like minus 1/2 to 1/2. Then we can use the like so since the gamma is larger, then we need more measurements. And then we can define the minimization of gamma to be some virtual resource distillation overhead. So here the minimization is over like any choice of the lambda plus and lambda minus as well as their coefficients. And the minimum possible gamma will give you the kind of the overhead for the virtual protocol. So in this case, we could define the virtual distillation rate. So here, comparing the definition to the conventional distillation, since we need since the overhead makes the measurement measurement outcome much larger, so we need like more measurements. Then we need to normalize the m copies by the c squared. Why we need the c squared? Because this generally comes from the from the Xiao noise or statistics requirement. So for example, we can prove that based on the Hoffman inequality, and suppose we want to obtain the virtually distilled outcome to accuracy beta with probability 1 minus delta. Then so the number of copies of rho we need is this one. So here this part is the conventional part, and here the 1 over rate part is kind of the so it depends on how efficient you can obtain the state. So actually this so the number of copies of the rho is actually the same for the conventional definition. So this is why we normalize it by the c squared. Right. So here we kind of formalize our definition. We by linear combination of free resources, we could define the virtual resource distillation. And actually, we can easily show that the virtual distillation is definitely more powerful than the conventional distillation, right? Because here we can always choose, for example, lambda minus to be 0, and then it just goes back to the conventional resource distillation framework. Then the question is, will virtual distillation be more powerful than conventional distillation? And to study this, we need to estimate the virtual distillation rate or the overhead. So actually, based on the definition of the virtual resource distillation rate, we can find that basically, or essentially, we need to estimate the virtual distillation cost or overhead. So here in the following, we focus on how to estimate the overhead. And in our work, we provide two approaches. The first one is based on, so we convert the overhead to an optimization problem. And in many cases, the optimization becomes efficiently computable SDP. And the second approach is based on, so we convert the overhead to the some resource measure, which is the maximum overlap with the target state. And so we give also the operational meaning to the overhead function. So yeah, let's then move on. How can we kind of characterize the cost overhead? So for the first approach, we consider an optimization problem, which is defined in this way. And actually, there are different versions of it depending on the definition of the free states or the property of the target state. So there's another version of it, theta G, and so it's a kind of a slight change of this optimization problem by replacing this one with this constraint. So these two optimization problems, they are generally convex optimization. And in many cases, if the free set of states or objects, if they are like a convex combination of like finite a small number of states, or if we can characterize them efficiently, then there will be SDP. So here we have this SDP, but how can we relate to the overhead? We need three different definitions of the resource measures. So one is the generalized robustness, the standard robustness, and the resource fidelity. I will not go into the detail, but so here is our result. We can show that the resource virtual distillation overhead C for two different cases. One is when the robustness is not infinite, like entanglement or magic, and the other is when the standard robustness is infinite. So in this case, in many cases, we have that the overlap of a free state and the target state is a constant, such as coherence. So for two different cases, we have two different bonds, but overall, you can see that they're quite similar. So just replace this S with this G. And here we have some parameters, which depends on the resource, the amount of resource of the target state. So here on the upper bound is the robustness, and the lower bound it uses the fidelity. So it seems they are kind of quite not still kind of unrelated. But actually, we could further show that in many cases, the upper and lower bound, they actually coincide. So for example, for many resource series such as entanglement, we could show that this part equals this part if we consider the Bell state. And in other resource series such as coherence, we would also have this part equals this part. So then it means that in many interesting resource series, we would have that the upper and lower bound they coincide. So then we get an exact expression for the overhead, which is this one. So if further that the set of free states, they are easily, they could be characterized efficiently, then we can, it means that we can calculate the virtual distillation overhead efficiency, at least for small systems. So this is the first approach. The second approach is to relate the overhead with some resource monotone. So here the resource monotone is the maximum overlap between some free operation applied on the state and the target state. Actually, this resource monotone, they could be computed exactly in many cases, especially if we have a free generalized Turing operation. So it means we could apply some free operation to the state, such that the state will become a combination of the maximum target states and some free states. So based on this result, we can show that when a free generalized Turing operation exists, we can make use of the generalized Turing operation to design the virtual distillation protocol. So we can show that the cost will be like in a much more in a very explicit way. So it's inverse proportional to the maximum overlap of the quantum state. And so the natural question is when the generalized Turing operation exists. So in this paper, they show that when this condition holds, the generalized Turing operation exists. Then it means that when this condition holds, so when this condition holds, we could also analytically relate the overhead with the resource monotone. So here we have two results, but they are kind of complementary to each other. So the first one provides an exact characterization of the virtual distillation overhead with some explicit SDP, and here we do not need to optimize the free operations. While theorem 2, actually, it is applicable to general sets of free operations. So as long as you can construct the generalized Turing operation, so it's applicable to like in addition to resource non-generation operations, we could also consider like less artificial definitions. So they are actually complementary to each other in practical cases. So these are the analytical results we have, and here we want to show that virtual distillation actually indeed they can help. They can they are much better. It is much better than the conventional resource distillation. So here we consider 3 resource frameworks: coherence, entanglement, and magic. And the target state, it is the maximum coherence state, the UPR pair, and the magic state. And for coherence, we consider the maximally incoherent operation and also the defacing covariant incoherent operation. So we can actually calculate the virtual distillation overhead and also the virtual distillation rate and compare it to the conventional distillation rate. So there are works for the conventional rate. And for entanglement, here actually we can consider the separability preserving operation, but actually we can also consider more physical operations such as LLCC. And we compare our the virtual distillation rate to the conventional single shot entanglement distillation rate. So for the conventional rate, we just consider the largest set. And for magic, here the free operation, they are the stabilizer operations. This is the result. So here, this is coherence, entanglement, and magic. So for example, for coherence, you can see that there are many different lines. Actually, for each of the lines corresponds to the smoothing parameter. So here, this right one is the 0 smoothing, and then you have a like larger smoothing. So for the dashed line, it corresponds to the conventional distillation rate. Since the coherence is so for example, for the right one, since the smoothing parameter is set to be 0, then it can only distill a maximum coherent state if the noise, the P corresponds to the white noise we add to the coherent state. So as long as the P is not P is the 1 minus P is the white noise we add. So as long as the noise is non-zero, then we could not distill any coherent state. But with some smoothing adding into the state, then we could distill some coherence, right? So for the single shot case, for the conventional case, you can see that the distillation rate it is a very not continuous, right? It's kind of jumps suddenly because of the conventional no-goes or the conventional definitions limitations. But here we consider if we switch to the virtual distillation case, we can see that the distillation rates, they are much more smooth. So here we have 3 cases depending on how many coherent states we want to distill. But in all of these 3 cases, we can see that they are much more continuous than this than the conventional case. And especially even when for this part where conventional distillation has a 0 distillation rate, but we could still have like a smooth distillation rate. So it happens similarly to the entanglement and also to the magic case. Yeah. So at last, I want to summarize and conclude a little bit. So in this work, we introduced the virtual distillation. It's a kind of a extended and also experimentally friendly framework of resource distillation. And our result, essentially, it combines 2 ideas. So one is conventional resource manipulation, and the other is classical linear post-processing. And in addition to the general framework, we also derived computable semi-definite programming for estimating the overhead and show that it is linearly related to the inverse of a resource monotone. And our result is applicable actually to general resource theory, even though we only showed its application to state resource theory. It's also applicable to quantum channels and even super channels. There are many interesting future works. I just list 2. So one is that it is very interesting to see that whether virtual distillation still has advantage in the asymptotic limit. So here we show that it has advantage in a single shot case, but if we have like many copies of the state, whether the advantage maintains is an interesting question. And also, how can we apply it to like specific resource series and consider practical applications in practical tasks is also very interesting to me. Yeah, that's it. Here they are the reference. Thanks very much.
Thanks for the talk. Any questions? Sorry.
What? So are these maps probabilistic free protocols like this lambda plus and lambda minus?
Actually, they are. So here, for the STP and the analytical analysis, they are deterministically freeze. Yeah, but so we actually have 2 papers. So one for the main result and another parallel one. So for the parallel one, we define. So we consider that the lambda plus minus they could also be probabilistically free. Yeah. Actually, if you consider probabilistically free, then you have even further advantage. Yeah, but the definition will be more complicated. Yeah. Next.
Yeah, there was another question here. I think.
It's a very naive one, but typically we consider like we distill something and do something quantum with it and then measure it, right?
Yeah.
Can you like apply this virtual distillation scheme even for those scenarios? For example, like if we want to distillate maximally entangled state, and then like do the adaptation or whatever, and then like measure something.
Yeah.
In those kind of scenarios, can you also do this?
Yeah, actually, I think what you just talked is exactly our scenario. So we just assume that if the state is measured, then you can always make use of virtual protocol.
Oh, but I was meaning that like you are directly measuring the state you distill.
Yeah.
But suppose that you want to use this for some.
Yeah, it's the same. So here actually the figure indicates that we directly measure the state, but actually you can manipulate the state furthermore. So you can like have some ancillary qubits, make some joint operation. It's fine. So it still works for that more general scenario. Yeah. Thanks.
One more question here.
Follow up to the previous questions. So as far as I understood, you have not restricted your measurement basis.
No, yeah, it's
So
yeah,
will
general.
there be further gain, say if you restricted your measurement basis to measuring the stabilizing basis, would there be further simplification or would it not change the results?
Yeah, so here we assume that M is arbitrary measurement. So the virtual protocol should be applicable to any measurement.
Yeah.
But if you assume that M is a restricted measurement, my intuition is that it should definitely have some further advantage. So, for example, if we consider the stabilizer formalism, and if you just want to simulate for example, like if we, because if we consider entanglement in the stabilizer formalism, the maximum resource is also a stabilizer state. You can just simulate the measurement outcomes using that stabilizer state. Right, so everything is classical, so you do not need. Yeah. Yeah, I think it's a very interesting question. So if you restrict further the set of measurements, whether you have further about, yeah, I think it's very interesting.
Okay, I don't see any more questions. Then, yeah, thanks again for the talk.